Ik denk het wel, ik ben nu dus nog even de livestream aan het testen. Test. Right, livestream lijkt te werken. Dat is goed. Dan gaan we straks aan mensen.
Ja, zo meteen beginnen als we beginnen uitlopen. Wil iemand nog geslaagd worden?
Ja, dat is misschien wel handig als jij dat kunt doen.
Ja, en het SD-kaartje vervangen?
Ja, maar dan moet ik normaal gezien maar één keer en dan ga ik over de middag doen.
Oké.
Normaal gezien.
Ja.
Wie rol moet zijn. De camera moet wel scherp zijn.
Is goed zo.
All right, let's start. Say hi to the 6 viewers on the live stream. Hello. Welcome all to the first ever QUIC Symposium 2019. Before I begin, a small reminder, we do have a code of conduct on the bottom of the website, and we expect everyone to honor it, and we are prepared to enforce it. Of course, that will not be necessary because we're all very nice people here. If you've missed the practical information sheet, it's pretty much the main thing you need to know to get on the Wi-Fi. We have a nice filled program today. Very predictably, when I said to people that we had a lack of talks, the talks started to stream in abundance. So now we have 10 talks, which is fantastic. I've planned them all back to back early on, and then the idea is that you then know what everybody else is doing, what they can talk about, and then in the afternoon we will have kind of In the IETF, they would call it unstructured time, so time for some extra discussions, maybe in group, maybe one-on-one. I don't really have a plan for the afternoon after 3 o'clock yet. It'll kind of depend on what you guys want and what you find interesting. Let's hope we'll see what it does from there. I also think the afternoon break will be a bit earlier or maybe overlapping with some of the discussions as well. And then some people can join us for the dinner afterwards. Like I said, we have 10 very nice talks. Because we have so much time for discussion afterwards, I'm going to try to keep the amount of questions per talk to a minimum. So we can ask a few questions, but it's not the idea that we're going to discuss after each talk directly. So let's try to keep everything nice and close together. As you can see, we have 9 very excellent talks for you and 1 very mediocre one at the end. So it should be all very interesting. The rest of this introduction is going to be me introducing the people present here. I'm not really a big fan of just reading what's on slides. I think it's quite boring, so you can read while I try to make it a bit more interesting. Sadly, I have to begin introductions for someone who is not here. I started preparing the symposium together with Oliver. He was then at Aachen. He recently got promoted to a full professorship at Brandenburg University. And he has been so swamped with his work there that he sadly couldn't even attend his own event. But he's still very interested in QUIC and talking to you about QUIC. And he will try to watch Livestream as soon as this lecture today ends. That means you are all now stuck with me, which should be okay. I might bore you a bit with talking about logging and tools. If that is so, please let me know and I'll try to tone it down for you a little bit. Let's see who we have next. Tim is not yet here. He had a small emergency with one of his kids, but he will come. Tim is a very interesting guy within the web performance community because he not only he works at Akamai, one of the biggest CDNs, he also has his own very popular website. So any new web performance technique that comes out, he can immediately implement it in his own website, and then he shares his insights from real users with like everyone on Twitter. So he's a very interesting guy to follow, and he will share some of that experience in his talk in the afternoon as well. Second one is also not here yet. It's Maarten. I did my first summer job in IT with Maarten here. I'm very happy to have him as a colleague right now, because Maarten is a very good researcher. He is extremely good at writing English papers and reviewing them for me, which is great. He's also a very diligent researcher. If you have need for someone to work with you on a paper on video streaming, look no further. This is your guy. Then we have Mirja. I can only say I'm very impressed. I think we are about the same age, yet she has a PhD, has done some very interesting research. She is an area director at the IETF, and she's written a whole bunch of the QUIC drafts, or co-authored a whole bunch of them. So, and she was kind enough to give me the opportunity to present my work at the IETF just a month ago, for which I'm eternally grateful. She is, however, a bit private. She didn't want to share her contact information.
I didn't see that, sorry.
I'm sure if you talk to her directly, you can get something out of her. Next was Maxime. Maxime is an absolute unit. I was doing some work on QUIC tooling and debugging. I wanted to present it at the IETF remotely. And I asked him if he could add support for it in his tool. Maxime is doing a QUIC tool of his own. And he added that in like 1 or 2 days. Amazing. And then the third day, he came back to me and he said, you know, I did some more testing and I found a remote code execution exploit on your tool. You know, going above and beyond kind of describes Maxime, I guess. And with Francois, I sadly do not know him all that well. We haven't had the time to talk all that much. I hope that will change later on tonight because we're going to dinner together. But I've read his paper on forward erasure coding, forward erasure correction, and it was very interesting, and so will his talk be. It's quite similar for Quentin, okay, I'm sorry. We haven't had a chance to talk much, but his topic is one that I know relatively little about, but I think is extremely complex. So I'm very interested in hearing what he has to say and share with us today. Now, with Jonas, Jonas did his bachelor's thesis with me last year. He worked with me on the initial QUIC tools that we made. And he had a lot of work putting into parsing output format logging for different QUIC implementations. And it's because of all the trouble he had with that and keeping that up to date that I started the QLog specification. So if I talk too much about logging, it's really Jonas's fault. You should blame him. Sadly, Jonas does not learn from his mistakes, because he has also indicated that he might want to do his master's thesis with me. Which is not a good idea. But thank you for hard work. Then we have Wouter. Wouter has done a slew of very different projects here, gaming, networking, and now AI and image processing. The nice thing about that is he always has like a new perspective on things. Whenever I give my papers to Wouter to review, he always comes up with like a new way of looking at things, some new comments that nobody else can give me. So thank you for thinking out of the box and being a good colleague. Tom is currently working with me as a bachelor student doing HP3 work in our own QUIC implementation. He is also going to do a summer job with us in July and August, working on QUIC tooling and visualization. So you'll be seeing his work down the line. Sven is a very brave man. He came to me looking for a bachelor thesis again in something with QUIC. And I said to him, you know, congestion control is very interesting, but it's quite difficult. It's probably a bit too difficult for a bachelor's thesis. I told him about that 3 times and he still wants to do it. And he's doing it now. And it's not always going as easy as we had hoped, but I think he's doing a really good job and trying to understand a very complex topic that I myself don't really understand all that well yet. Then we have Joris. Joris, I have him as a student in one of my Internet of Things classes. And he and his group have the topic zombie apocalypse, where they have to make devices that have to deal with low power availability and not always having a network available, that kind of thing. And the thing they did was, it's supposed to be fun, right? It's a zombie apocalypse. So they wrote a story where the whole of the university is overrun by zombies. Only the EDM here is the last bastion of mankind. Of course, the first person they sacrificed to the zombie horde, yours truly. So thank you for that, Joris. Luckily, he's also a very smart guy. He's looking into video streaming and especially doing in-network measurements to optimize the streaming. And he's also trying to do a PhD in that with us next year. So let's hope that comes true. Then we have Jan. I met Jan in January. We went to Aachen and I presented some of our work on QUIC. And then I also presented what I would like to do with QUIC in the future, in the longer run. And all the while, Jan was sitting there, you know, like this funny little smile on his face. And after that, he just said, you know what, the thing you wanted to do, we already did it. You know, I already wrote a paper on this. So that was not cool. Yeah, not cool. And then to make things worse, we did the symposium. You know what he said? You know, I'm going to take that paper and I'm going to present it at the symposium, just to rub it in. So you're lucky that it's very difficult to stay mad at you because you are such a smart and nice guy. And I'm really looking forward to the talk. And with Konrad, we also met him in January, completely blown away by his presentation. He's doing PhD level work for his master's thesis in a very difficult setting in human perception, which I always think is quite challenging to research. He's doing it quite well. We will also have a presentation on that today. With Jeroen, I met Jeroen a couple of years ago. We were together in a research project on HTTP2, right? That used to be the big thing. It's all past now. And he did some very interesting work speeding up video streaming by combining server push with very small video fragments, trying to speed up the start time, which I always thought was very impressive research. He also has some very nice demos at the end of the project. Jeroen was kind enough to come here today and see if QUIC might be something he's interested in. Now, Emilia, I've been chatting with her a lot as she is trying to integrate my very badly made tools into her research. So she's asking me a lot of questions, and from those questions it's very clear that she really understands what she's doing, that she's also working on congestion control, and it's very difficult, but she really understands it, And she's just in her first year, so I really expect a lot from her research going forward. And I hope she gets to learn a lot from people smarter than me today. We have Torsten. Last December, I went to CONEXT all by myself. First time, I didn't know anyone there. And Torsten was kind enough to take me under his wing, show me what's what, and introduce me to everyone there. He only tried to get me drunk 3 times, which was nice. But so overall, Torsten is a very nice stand-up guy, and one of the only persons in the world that actually has a founded opinion on HTTP2 server push, which is quite rare to find. With Mirko, whenever I meet Mirko, I feel like I have to apologize to him because I asked him some very difficult questions at CONEXT about his paper. What do I want to say? So I'm sorry for that. I'll try to rein it in today, and I'm looking forward to your talk. Yeah, with Hendrik, Hendrik had one of the most impressive master's thesis that I've ever seen here. He's done some really cool work streaming 360 video in a light field setting. If you want to view a really cool demo today, ask Hendrik to take out his laptop and show you some of his work. It's really quite impressive. He's also going to try to do a PhD thesis with us next year, and maybe QUIC will feature a little bit in there for doing the actual streaming. Not just the video, but also virtual reality and 3D objects. Then we have Mariano. Mariano is suddenly figuring out that it was a bad idea not to upload a picture. But Mariano is organizing a Capture the Flag event here at the university next week, so I'm sure he'll find a way to pay me back for this. Mariano is an incredibly prolific researcher. He's only been with us for 6 months, and he's done an amazing amount of work. A lot of work of which I say, when he comes to me with a concept, I'm saying like, there's no way this will work. I don't understand how this works. And then a week, 2 weeks afterwards, he has a prototype and it works. It's very interesting working with it. And with Eric sadly could not be here today, but he will give a presentation remotely. It's the first presentation. He is, again, one of the very prolific researchers. Maybe that's something that their security guys have in common. I don't know. He has a huge amount of papers on TLS 1.3 and how it interacts with QUIC and all the things that we might improve from that. So that should be a very interesting talk as well. Then we have Dan. Dan is my current master's student. He also was my bachelor student. He worked on HTTP2 tooling. That's where it all started for me. He also didn't learn from his mistakes, so maybe Jonas should talk to Dan, try to prevent this from happening again. Dan is amazing in that he just took the Chromium code base, like one of the most complex and large code bases known to man, and he's trying to put QUIC into there. He's had a lot of problems trying to combine boring SSL and open SSL, but he's gone through with flying colors, and he's now working on his own HTTP3 implementation and asking some very difficult questions of the QPAC team in the last few days. So it's very nice working with that. The last one, I think, is Mike. I don't know Mike yet. We briefly met as well in January. But Mike is basically here, as you can see. He doesn't really have an interest in QUIC. He's just here because, a nice day off, sponsored by the university. Why not? But maybe he will find something that really tickles his interest today, and he will be a force to be reckoned with within the QUIC community in the years to come. Whew, that was it. I think we have 2 people that did not supply slides. I don't know if you want me to introduce you or not. I'm talking to Timo.
No.
You want me to introduce you as well?
If you can.
Okay, so we have Timo and Ekaterina. Which I also don't know. I never heard of you before, I'm sorry to say. But they have very interesting things. They're working, as I understand, on a network simulation environment, which looks very impressive, and they're working on adding QUIC support to that as well. And they are interested in doing a packet drill implementation, which should be interesting for Maxime. And they're also interesting in visualizations and logging, which would be interesting for me and for Mirja probably as well. So very happy to have you two here as well. I think I have everyone here then. So thank you to our sponsors. We will have free lunch. Sadly, there is a problem with the free lunch. The free lunch is only for people that fill in our QUIC survey. So we're running a survey on QUIC, trying to figure out the different use cases that people would want to use it for, and which of the features are actually very important for those use cases. So if you have some time, if you have some interest, feel free to fill that out so we can have a nice paper at your expense. And that's it. And it's right on time. So unless anybody has any questions at this point, no? Thank you. Then I will try to set up Eric's talk, which I first need to disconnect the HDMI, connect the audio, then reconnect the HDMI, because it's Windows. So let me see if that works. Seems to work. Seems to work. Good. Reconnect HDMI. Fantastic. Let's see if that works. Hello, Eric. Hi. Aha, fantastic. I'm just gonna change the volume here, if you can talk a little bit.
Okay, can you hear me?
I think so. Try again.
Can you hear me?
Yeah, I think everyone, yeah, it's fine.
Yeah, cool.
That's great. And I'm just gonna, I just gave you a nice introduction, Eric. Everybody knows who you are now.
Very good. I still need to set up the
There we go. It's a bit small here. No, that should be fine. Yeah, I think that's fine. So I'm gonna give you the floor. Have fun. As an exception, because Eric can't be here, we will allow questions after his talk, obviously. So I think he's prepared a talk of about 20 minutes, and then we have, let's say, 10 minutes for questions. So Eric can also get the most out of the experience. So Eric, thank you very much, and the floor is yours.
Hi guys. I'm Exil from the University of Hamburg, and I want to talk about enhanced performance and privacy for the QUIC protocol. So, what's the motivation? I feel like the connection establishment presents nowadays a performance bottleneck on the web. That clients usually have a lot of bandwidth available. However, the delay of the connection establishment is so large that we usually do not separate this available bandwidth, which leads to bad performance, especially web browsing. And another problem which I worry about is that network-based attackers, such like the NSA, might have an interest in looking at the client's data and attacking its privacy. So I want also to protect against this. And finally, I also worry about online trackers. And I think a transport protocol should, QUIC, should also protect against those to the best possible extent. So first, I start to talk about the cryptographic handshake. Afterwards, I will talk about the transport handshake. So let's start with privacy issues and finding and the cryptographic handshake of QUIC. There is certainly the user tracking via TLS session resumption, one which IETF QUIC is at least affected of this, because the TLS session resumption is a performance improvement which reuses a connection state of a previous connection. And it always requires that the server can correlate the user to the previous connection. However, also QUIC, Google's QUIC version, has a tracking mechanism within its cryptographic handshake. This is the server config. The server config is provided to bootstrap the cryptographic connection establishment, and it can contain a unique identifier for each client, and the client usually saves this server config across various connections, and thus it's absolutely feasible to track the client via this server config. So I did quite some browser measurements, investigating Chrome or Firefox, and found that they do not really protect against these tracking measurements and need improvement. So, yeah, so much for this privacy issues. Now, let's investigate the performance improvements which are available for the cryptographic handshake. There is idea of TLS resumption across host names. Nowadays, when we visit a website, let's say, and this website includes some resources from static.example.com. Then our browser would establish two TLS connections, one to example.com and the other one to static.example.com. However, these both subdomains might be operated by the same entity, and thus these subdomains trust each other. So sometimes they even share the same private key of their TLS certificate. Thus, it makes, from my perception, sense to have session resumption across these host names which share the same private key of the server certificate. And in a paper, I showed that this can lead to a performance improvement by up to 30% for the connection establishment of an average website. And another performance improvement is which only is valid for QUIC, is that we serve the server config not in a separate round trip with the QUIC server itself. However, we could also distribute the server config via DNS. Cryptographically, this is totally fine, as we don't trust the transport this way, and this could also lead to saving around the time during the initial handshake. So I was asked to also visit shortly the security aspects of the TLS resumption across host names. Nowadays, there exists a very similar concept, which is HTTP2 connection views. It is not session resumption, because session resumption requires the establishment of a new connection. However, it is reusing the same connection across different host names. However, it always applies to the same physical server. So, if you are interested in some security problems of this, please have a look at RFC 8336. And attacks which can be derived of this if the client accepts an untrustworthy server certificate. For example, if you are at an airport and you want to log in and you manually have to accept a provided certificate of capitalportal.com. And now it might be the case that this server certificate also includes additional host names, for example, example.com or google.com or twitter.com. And later on, the client might tend to connect to these other host names, like for example, in this case, via a zero RTT resumption handshake. And now a passive observer on the network can directly decrypt the client's zero RTT request. Another attack which is feasible in this setting is if the browser does not carefully validate others' TLS extensions before doing the resumption. This is especially important in the case of a PIN server certificate. So assume that we have a hostname example.com and another hostname hint.example.com. And now it might be the case that the client connects to example.com, receives a server certificate which is also valid for hint.example.com, and then the client is able to have a resumption to hint.example.com using the session of example.com. Thus, that he is not using the PIN server certificate in that case, which is also a security problem. So let's talk about the transport handshake. There, privacy problem at hand are validation tokens. So these tokens are used to prevent denial of service attacks. And the client in the QUIC and IETF QUIC, the client stores them across several connections. And this allows the server to link these different connections to the same user. And this is definitely a privacy problem. And as there are quite a lot of researchers in the room, there's, to the best of my knowledge, this unaddressed research problem. It's the question whether we can construct tokens with better privacy properties than at the moment. At the moment, maybe a token is constructed by encrypting the client's IP address. However, for the server, all he really needs to know is that the client had a previously successfully established connection to the server. And another thing which needs to know that the client is not replaying the same token a couple of times. So if I say construct tokens for better privacies, I'm thinking about something like blind signatures, which are also from cryptocurrencies or from e-voting applications. And it would be nice to have some similar privacy properties for these tokens. However, this is future research, and if anybody is interested to work on it, I'm happy to share some ideas. Let's talk more about performance improvements for QUIC's transport handshake. And here I investigated especially the concept of address tokens. And the first idea is that we do something very similar to resumption across hostings, that we say, okay, when I can share the resumption handshake across several hostings, why not do the same with address validation tokens? So one server says, okay, I had a successful with this client, and the other server is accepting this issued token, and thus the client does not need to have an additional round trip with the server during the connection establishment to validate his own IP address. So this concept is, however, limited, as it only provides benefit to 60% of the connections during an average website to people. This concept with a broader scope would be to issue these tokens out of band. This means that, for example, to have a DNS resolver to issue address validation tokens. This concept is very easy to realize for Google or Cloudflare, as that they have their own DNS resolvers, and they, I assume they trust the operation of these DNS resolvers, so that they can directly trust the DNS resolvers to issue the tokens. Yeah. However, I want to have this on a, well, I would like to see it on an internet-wide scale, so that there's everybody that likes to can allow a DNS resolver to issue valid address tokens for the service. And compared to the previous setup, or to the other points above, this concept only provides token with a very low priority to the client. Thus, the client would only use these tokens if the client has no other tokens available. Because the client does not authenticate that these tokens are issued by a trustworthy entity, that there's a trust relation between the DNS resolver and the website. It's just an opportunistic use of these tokens to do the address validation. And there are also some additional research questions involved in this concept, which I want to share. It's quite difficult to do the key management in this setup. We have a web server to allow various DNS resolvers to issue valid address tokens, and if they abuse these tokens, they will also invoke this trust. Plus, I think it's quite a lot of research questions are involved in having a designated protocol handling this key management. Yeah, and if anybody is interested in working on this together, I'm happy to collaborate. So, I think another performance problem which we see on the internet at the moment is that the TLS 1.3 is available on about 8% of the Alexa top million sites, at least as observed in this measurement. However, only a very tiny fraction of these sites support zero RTT session resumption. And the reason for this is that zero RTT session resumptions are per default they are per default not available within the TLS 1.3. This means that the operator of the web service has to enable it manually. And the reason why this is restricted, like this is that the security guarantees of zero RTT session resumption are much bigger than of one RTT session resumption or full handshake. We miss forward secrecy, and we are vulnerable to replay attacks. And this presents on the application here. So, however, within this month, on the Europe 2019, there will be presented a paper which exactly addresses this problem. And I would, well, at least I hope that this might change the way we use zero RTT session resumption in the future, as this proposal provides or shows a path towards forward secrecy and preventing replay attacks during zero RTT session resumption. So I come to my last slide. The web is still pretty slow, and we require much better protocols to make it faster. I think QUIC alone is not the answer to having a faster web. We still need to do a lot of work on the DNS to update DNS to today's demands on the internet. And the privacy protections against passive network observers, that they are well progressing, and I'm really happy about this. However, I feel that user tracking via online services remains still a problem, and we need to work on this harder to find a better privacy for the users. So I thank you for your attention, and I'm happy with your questions.
Just thought that it would have been more logical to rotate the webcam so that Eric can actually see everyone. Can you see everyone now?
Yes.
Okay, so we have a nice audience, and they're gonna redo the applause. Okay, so we have time for some questions. Let it rip. Come on, guys. I think he uses a shout, and if he doesn't understand, I can repeat.
Okay. So when you do session resumption, you usually already also cache some transport parameters and stuff. So are you thinking that this information should also be stored in the DNS, or you just use default parameters, or did you look into that at all?
Can you repeat the question?
The question is, if you do session resumption, you typically also cache some transport parameters, right? And the question is if you would also cache those in the DNS or the other proposed solutions that you have.
In DNS or within session resumption across host names? For session resumption across host names, that is definitely also a point that the transport parameters that you agree upon during the first connection are also somehow valid for the other host names you are connecting to.
Okay, does that answer your question?
Yeah,
I did not propose to do session resumption via DNS. That is.
but it's kind of the same mechanism you're using, right?
She says it's the same mechanism you're using.
It's good to understand.
She says it's kind of the same mechanism that you're using to session resumption.
Session resumption across hosts. Why it's kind of the same mechanism with respect to DNS? Or
So if you want to quick start the connection, basically, that means you send some data right away. That means you need some information about what the path would do, what the server is capable of. So you need kind of this information about these capabilities of those transfer parameters or whatever. I guess you can just run with the defaults.
Yeah. So I think basically this addresses more the case where I think that we can put the server config in the DNS to quick start the cryptographic handshake. And I think we don't really need, or we just use the default transport parameters during the initial handshake.
So what I'm saying is, I don't think it's an unsolvable problem. It's just something to look into and think about.
Yeah.
Thank you. Any other questions for Eric? All right. All right, Eric. Then thank you very much for the presentation.
Yeah, thank you.
Feel free to join us at the live stream.
Yeah.
And if anyone has any more questions, you can contact Eric directly at the email address. All right, thank you, and see you next time. Bye. There we go. Next up is Maxime, who I hope has HDMI.
Yes, I do.
There we go. Okay, great. Okay.
I guess I will start. So we can stay on schedule. So I'm Maxime Pirot, coming from UC Louvain, and I'm here to present you a tool we are developing in the lab, which is called QUIC Tracker, and it's an active test tool for QUIC. So why did we decide to make a test tool? Well, there are many reasons to bring a test tool to QUIC, and one of them is the QUIC complexity, the complexity of the specifications. And one way to visualize this complexity is looking at the number of requirements in the draft, so the number of must not. This is a graph of the evolution of those numbers of keywords, and you can see that since the initial spec, it has nearly tripled. Multiplied by 3, and also since the start of our study, it has increased by 30%. So, given that the spec is complex, there is an interest of bringing test tools to make sure that the implementations are working correctly. So this specification is complex and is also evolving quite rapidly. So you have, as vertical lines, you have the document publication time of the different drafts we studied. And also you have on the black curve, you have the number of test implementations that are taking part in the interoperability tests of the IETF working group. So you can see that, as expected, those endpoints are implementing the draft quite rapidly after the document publication. So you can see that. So this is the number of the maximum number of versions. I mean, the highest version that is announced by those test endpoints, and some are not active anymore, but there is like 12 endpoints that are still taking part in the implementation effort. So we choose to contribute to the QUIC effort by proposing an active test tool. And so this tool can be used against any server implementations because it exchanges packets to test them. So you don't have to rely on source code. You don't have to rely on being able to install the tool. You can use it through the internet, and that's actually what we do. We use it daily. There's a link to the website in the end. And we publish all the results of this test tool so we can track the evolution of those QUIC implementations. So the main result of the tool is one that you can actually look up online. So this is the result grid from yesterday evening run. And so on the x-axis, you can see different implementations of QUIC. And then on the x-axis, you can see different kind of tests. So I cannot show the name of all the tests because there are 28, I think, right now. And so I group them by area of interest, I could say. And so you have tests for the different parts of the handshake and different parts of the header, then tests for the acknowledgements, tests for streams, migration, and also HTTP3. And so each cells represent the results of the tests, which is classified in, here it's classified in 3 classes, so success, failure, and error, but you can actually have more classes than this, but just for visualization purposes, I limited it to 3. So success is obviously the test has passed. Failure is the test has failed, meaning that one of the requirements was violated, and error means the test could not be conducted because, for example, for HTTP3, if you don't allow unidirectional streams, then you cannot do HTTP3. So that's a requirement of the test, and those endpoints don't. So we can see different kind of things. So HTTP3 has some support. We have an ongoing issue with NGTP2 actually that we have to resolve. Some tests are failing. So those 2 tests I think are edge cases in our greasing tests. So we send greasing frames and stream times, and we just see if the endpoint supports it. What else can we notice? I guess that's it. So on the website, you can see all the names, and then you will see even more. But that's what I remember for now. Okay, so let's look a bit at the architecture of QUIC Tracker. So this is explained in details in our EPIC paper and in our EPIC presentation, but I will just do a summary. So basically, in QUIC Tracker, you have different kinds of components. You have a library, you have test scenarios that produce trays, and the trays are read by the sector, which is embedded in a website that you can actually see. We will focus on the left-hand side part today. So the toolbox is a library built in Go, which is designed to implement QUIC clients mainly, and provides a high-level API to be able to manipulate QUIC packets, craft them, read them, change everything inside. And so this library allows you to do all types of connection establishments. It handles streams, recovery mechanism, acknowledgements, obviously, and HTTP3. And it's about 5,000 lines, so 1,000 line more than in December. We've added a few things since there. Based on this library, we are building test scenarios. So each of the cells is a separate test scenario. There exist 28 of them right now. And so when we, so I showed you success and failure. How do we decide what is the result? Well, we look at the specs, we look at the must and the must not, and then we establish basic rules, basic scenarios to test a given feature and see whether the rules are respected. So if the server is required to do something, then we observe that if we test the given mechanism, we observe the given behavior. Each test is then executed in a separate connection, and as I said, targets a particular feature of QUIC. By no means the test suite is complete. There are plenty of must and must not that are not covered, and even then we could ask ourselves the question is that the approach to have to just look at the must and must not? We could have even more tests. And finally, each test is about 56 lines long, so it's quite, I think it's quite easy to write tests for a QUIC tracker. So those tests will produce traces, and I will not bother with the trace format, it's not really interesting. The idea is just that in the trace format, you have basic information, such that as the test passed, but you can also put specific data. So if you want to collect data during the test, you can put it inside the trace and then read it back later. And also, this is really interesting for interoperability. We record the packets that are exchanged, both in a PCAP format and in our own format, which allows us to use our own dissector. So the main idea of the architecture is that basically you can take every box that you like and replace the ones that you don't. So if you don't have use for the dissector on the website, just don't use it, and then use the trace and then put something after if you want, CLI tools, I don't know. And if you want to reuse the toolbox to do something else, I really don't know, you can use the two separately. So now I will recap the recent improvements of since December, and then I will review some of the future prospects for the tool. So we are obviously supporting the latest draft, as you have seen on the grid. We are basically handshaking with most of the implementations that are online, if not all. So this is a simple bullet line, but it requires a bit of work, obviously. We are currently phasing out the HQ-based test in favor of HB3. So HQ is just a protocol that has been agreed for interrupt testing, and it's just basically pipelining HB09 into bidirectional streams. And so this will not be supported on the internet, obviously. So we are trying to adapt all of our tests to use HB3 so that we can then run them against any server that would completely support the QUIC spec at least. So we have been also working to ease the development of test scenarios. I have a slide on this just after, but basically we reduced the number of lines per test by 9, and that's not just by putting smaller tests that would make the mean eliminations. We also simplified a bit mechanism. And so we added five more tests, mainly during the last ATF. We have a test for the spin bit support. We have a test that does IPv4 to IPv6 migration. We have the two HB3 tests, greasing test I've been talking about, and we have a test that violates flow control and check the server to notice it. So one thing we've been trying, which was not really successful, is bringing declarative programming to QUIC Tracker. So the reason behind this is, so there was discussion within the ITF about having a tool to write test scripts, and currently QUIC Tracker is imperative. It's imperative programming, which may not be the most natural way. And declarative programming seems a good fit for test suites, actually. So you just state what you want, and then the code does the job. It's very easy to read and supposedly easy to write too. So, for example, there are examples in the QUIC ecosystem that use declarative programming. QUIC Go uses Gomega for its own internal test suite. Gomega is just a framework to do declarative programming. So let's look at an example of what I tried to do. So this is a piece of code from a test. And it's basically, the purpose of this code is set a Boolean to true if the packet contains a crypto frame that has an offset of 0. And this is the way to do in imperative programming. So you just take the packet P, you iterate over all crypto frame, and then you cast them because you're using Go, obviously, and you check this offset to be 0, and then you set your Boolean, and then you break. The way to do it using Omega is this one. So you set first crypto, the variable, you define it to be equal to the fact that you expect P to all the crypto frames in P to contain an element which match all the fields, and if there are more, ignore them, of this structure. So all the fields of something which is a structure which has a field called offset, and this offset must be equal to not 0, UN64 of 0, because you're using Go, remember. So this is a one-liner. It doesn't fit in one line in my slide, but this is a one-liner. But I was a bit skeptical looking at this example about the benefits of using declarative. At least in this setting, this was something that I could do easily do in a few hours. I was a bit skeptical, and to be honest, QUIC Tracker is already quite simple in terms of code complexity. You don't have many nested for loops and stuff like that. It's mainly configuring what you want from the library and then doing a few checks. So I don't think there is a clear benefit in switching to declarative programming to just get rid of imperative programming. And also Omega cannot be reused as is in QUIC Tracker because of several technical difficulties I can talk later on. But there are also another interest in changing the programming paradigm of QUIC Tracker, and this brings me to the future prospect. So just before going into this, QUIC Tracker is not my main research project. It's just a side project, but I think there are interesting research perspectives to do with QUIC Tracker, and one of them is instead of changing programming paradigm, you could also bring a domain-specific language. And this is what packet drill does. So packet drill is a test suite for TCP, UDP, and also IP stacks, I believe. And if you look at the packet drill test, I should have included them actually. Anyway, if you look at the packet drill test, you will see that it's quite clear to see what's going on, because it's a mix of visual representation of the TCP segments and basic C system calls. But I think we can all agree that QUIC semantics are far more complex than TCP. So this is an open question, open research question. So can we invent a syntax that is rich enough and useful enough to express them? Because in the end, if we invent a syntax that is just another programming language, I'm not sure there is an interest in this. I'm not sure either that packet drill is incomplete, but that's not the point of that. That's not the point of this slide. So this is one thing we could do with QUIC Tracker, I think. I've gave to this subject a few thoughts, but I've not been successful yet. So if you would like to collaborate on this, I would be really pleased to do so. So one obvious one is also testing QUIC clients. So in the grid I show you, we are testing servers, but clients are the other half of the connection, so we should test them too. So how to make QUIC clients connect to you? Well, we could use advertisements on a popular website. Actually, none of you maintain a popular website, I think. By popular, I mean a huge website. Oh yeah, good then. Then we could do it later. So yeah, we could use advertisement maybe to make clients connect to the test tool, but then we have to be careful not to mess with the client too much, because they're expecting something to be served in the end. And also how to distinguish between the clients that are connecting to you. So if you encountered a faulty client, how do you report that this client was faulty? If it's doing HTTP3, maybe you can look at the user agents, but maybe there are other means. So this is another things we could do. This was brought by someone on GitHub actually. the idea is to use QUIC Tracker against a reference server from different points in the internet, from different devices. And by doing that, we could try to map the QUIC usability in the internet. So we could report basic UDP blockage, but we could also detect more advanced middle box interference, maybe because we have different test scenarios that produce different network behaviors, different kind of packet size change. So for example, if we do, is connection migration supported in this network, and those kind of things. I think right now it's too early to observe this kind of behaviors, but maybe in the future they will appear. And so to do so, a mobile deployment of QUIC Tracker would help the data gathering, obviously. And finally, also, so in the past 20 or 30 years, there have been several works that study TCP deployment and configurations. And so those measures or similar measurements could be also conducted for QUIC. And so, for example, measuring the initial congestion window that is configured on servers. I think this is something that we can do with QUIC Tracker. Actually, I'm trying to do it these days, and there are maybe lots of other things we could also study. So acknowledgement strategy and that kind of stuff. And this is research that you can do with QUIC Tracker. So QUIC Tracker is free. Its development is happening at GitHub, and you will find all the test results on the website. And there is also a tutorial on adding new scenarios, but if you need help to get started with QUIC Tracker, just talk to me, and I will be happy to help you. Thank you.
We have about 5 minutes for questions.
Yes.
Quentin can set up.
Thanks for the talk. So regarding you showed this great revolving implementations and all the tests that pass, fail, or there's an error. So what is did you obtain any feedback from some guys that do this professional, like the move fast implementation, for example? There are paid guys doing this implementation, and there are some errors with respect to your test case. So if you get any feedback on maybe your test case is not that well defined, or this.
Yes, this sometimes happens, obviously. To be honest, I've not been so active lately to report on my own the test that fails. So usually what I do is I look up at the grid and then go to the QUIC Dev Slack and then just talk to them to see whether there's something wrong with my test or if their implementation is doing something wrong. But lately I've not been so active in this reporting duty. Yep.
I was very sad to see no mention of key locators.
Yeah, I'm working a bit on QLog right now, and actually I have some progress to show you, but that's it's not coming yet to QUIC Tracker, but it will at some point. I think the idea of comparing the QUIC Tracker point of view with the implementation being tested point of view is really interesting. And actually, I would like to get rid of the website I programmed because it's not a really good website, and it sometimes takes a bit of time to maintain. So a QLog front end for QUIC Tracker would be really interesting.
I agree. I was just wondering if it's. Because the way I understand it, you don't always do the full setup, or you don't always send out every single packet.
No,
right?
the thing is, my implementations is basically a crappy QUIC implementations if you use it as a QUIC implementation. But it is able to produce several test scenarios, and so it's able to produce several valid packet traces, but sometimes producing a full log and a full reasoning of what happened may not be complete, but then just logging what happened, what was sent on the wire may be enough.
That was kind of my question actually. Is that a QUIC implementation you have, or is a QUIC implementation only part of the tests, and like how complete is your own QUIC?
So at first, the test did most of the job. Now I have kind of, so every time I need every time I need to acknowledge packets, I have a part of my library that does it. And so I don't have to include the mechanism for acknowledging packets inside the test. I just say, okay, acknowledge every packet. I can disable some acknowledgements, for example, for certain tests. But I try to put as little as needed in the test and put a common mechanism like recovery and acknowledgements inside inside the library. And I have a fancy architecture which is doing message passing, and it's a bit complicated, but I can plug behaviors and unplug them if needed for certain tests. Let's say, so I can reuse code across tests without cluttering the test with unnecessary code with regard to the test intent.
It's not complete enough that you could run it as a standalone.
No, yeah, it's not complete enough. It's basically just doing client side. Thank you.
Thank you.
Okay, so I'm Quentin. I heard that Robin said that there were a lot of people interested in multipass, so here I am. I will present multipass QUIC then, in a kind of more tutorial fashion. So I will first explain how we design multipass in Google QUIC, the old Google QUIC, and some evaluation about the benefits of using multiple paths. Then we'll sketch a little on how it should like in IETF QUIC. And then we'll open some questions that we have and challenge we observe with a multipass. So why do we want multipass after all? So currently, QUIC assumes a single path flow, whereas the internet has multiple access points. Let's take, for instance, the smartphone that has both Wi-Fi and 4G. Or even if your computer, which is connected to only the Wi-Fi, can have both IPv4 and IPv6 addresses, and sometimes the network behind each address is different. So you can benefit from using both. So multipass QUIC aims to have two goals. The first one is, of course, aggregating the bandwidth of both networks. And the other one is about seamless network handover. So you can switch from one network to another one without having any issue, and still probing the functioning path as long as possible. So about seamless network handover, there are something which is called connection migration today in QUIC. So what is connection migration? It says that basically a QUIC is identified by connection ID and not by the 4-tuple use. So you can survive a network change. So you can switch from Wi-Fi to cellular while keeping the same connection ID and while keeping the connection working. And actually, IETF includes some mechanism to test that the path you are trying to create is the real peer you are talking to. But while those mechanisms are required to perform multipass QUIC today is only specified to use only one path and to stay on the same path. And it is not planned so far to use simultaneously multiple network access. So I will describe now the design about GQuic. I will come back to the IETF one later. So about designing multipath QUIC, the idea is to say, okay, a connection is a set of paths. And you can use the path after the handshake is completed. So let's take an example of having a client which has both a Wi-Fi and 4G paths, and then it wants to send a packet over the 4G, and the server receives it. How the server can know that the packet comes from the 4G path? Because you cannot rely on the 4-tuple, because you can change. And also, you want to know on which path the packet belongs to, because you want to have performance monitoring, you want to have some kind of loss detection, to have a congestion window on each pass, and so on. And so to solve this issue, what we do is we explicitly mark on the packet on which pass it belongs to. And this is made by putting a pass ID inside a QUIC packet. So actually the connection ID remains the same. The packet says explicitly, I'm on the 4G path, or I'm on the Wi-Fi path. And each path has its own packet number space such that it can evolve, each of them can evolve independently. So about the high-level architecture of multipath QUIC, it looks like you have a connection. Within a connection, you have the stream and the frame management. So the frame management is done at the connection level, and then you put your frames inside packets, and packets are sent on different paths. And on each path, you collect the metrics such as round-trip time, number of packet loss, number of packets sent, and you keep the packet number space, of course, too. And so how does a multipath QUIC data transfer looks like? Let's say that here you have your phone that sends an HTTP GET via the Wi-Fi, and then you can have the reply that comes both from the Wi-Fi and the cellular, with each of them having different path IDs. And then you can have the acknowledgement of both packets using only one packet sent on the Wi-Fi, because we want to keep independence between the frame management and the packets. So you can bundle multiple ACK frames inside a single packet that acknowledge both previous paths. So when you use multiple paths, you have the classical algorithms, such as the path management, the packet scheduling, and the congestion control scheme. So about the path management is, where and when are you creating your paths, and on which networks? So let's take the example of having two hosts. Each of them have two IP addresses. So to start the connection, it's easy. You just use one address and you start the connection, and this is the initial path. And then, how can it use the other addresses? To solve this issue, we introduce new frames, which is called add address frame, that allows, for instance, the server to communicate its IPv4 address to the client, that then creates the path in a full mesh fashion, so that here with each host having two IP addresses, you have 4 different paths. Okay, then packet scheduling. You have multiple paths which are created. Now, on which path are you going to send the next packet? And we apply the classical lowest latency algorithm first. So let's say you have two networks, one with 20 milliseconds of RTT and the other one with 10 milliseconds of RTT. If the congestion window is open, of course, you will prefer the fastest one. Also, you have the case that sometimes the latency is unknown. When you start using a path, you don't know what is the latency you will have. In that case, we decided to duplicate the packets until we have some information about the network latency. It will only last at maximum one congestion window, the initial congestion window. And also an important point about packet scheduling is that you schedule all the frames, not only the data frames. So if you want to schedule the frames which are related to the receive window and so on, you have to schedule them with your scheduler. And about the congestion control, so the issue with multipath is that you are using multiple paths, and these paths can share at a given bottleneck. And if you use algorithms such as QUIC, you will be unfair against single path protocols, like if you are using 2 paths on a bottleneck, and then you have a third single path connection that is going to, the multipath connection will take 2/3 of the bandwidth of the bottleneck, which is somewhat unfair with single path protocols. And currently we are using OLIA, which is the state-of-the-art in multipath TCP. So about evaluating multipath benefits, We compare multipass QUIC and multipass TCP, the state of the art in transport protocols. So multipass QUIC is implemented atop QuickGo, and the implementation is open source. And we compare it with the Linux implementation of FPTCP in a mainnet environment with 2 different paths. So first, to evaluate the bandwidth aggregation, we exchange a large file over a single stream, and we collect the time you need to exchange the file. So the approach we take to evaluate this is an experimentalism approach. So the principle is to have a parameter space of bandwidth, of latency, of buffer size, and of losses. And then you sample this parameter space with a filling algorithm, such that all the points you will have will cover as many possible cases you could have in that parameter space. And so in this case, we have 253 network scenario, and we vary the first pass, so we have twice the number of scenarios we have. So to have also to quantify the benefit of aggregating, we compare the performance of the multipass protocol versus the single pass one, and we range it between -1 until 1. So -1 means that, yeah, multipass does not work. You have no good output. If you have 0, it means that multipass performs as good as the best single pass you could use. And 1 means that you fully aggregate both paths you have available. And of course, because you have some latency with the handshake, the first pass will have some importance on the result, especially with multipass TCP. And so this gives these results with multipass TCP and multipass QUIC. So the left box plot is using the best path in terms of latency, and the right one the worst. And we observe that regardless of the first path which is used, in 77% of the cases with multipass QUIC, using multipass, even the worst path first, provides better results than the best single pass protocol. So if you start the single pass protocol on the best path, you will always have better results by using the multipass variant. And you have better results with multipass QUIC than with multipass TCP. And of course, with losses, we keep the same trend with multipass QUIC, which tends to perform better than multipass TCP. Also, there are other works that look at the performance of multipass QUIC in real networks with Wi-Fi and LTE, and they confirm that using multipass QUIC still achieve to aggregate the bandwidth. Okay, so this is for the bandwidth aggregation stuff. Then we have the other use case, which is the network on the verge support. And actually, the largest deployment today of multipass TCP is iOS phones. Why? Because Apple found interesting to integrate Siri, multipass TCP in Siri, to support the Wi-Fi to cellular on the verge, to keep the connection running without restarting it. And so we somewhat mimic this use case with a request response traffic, where we send small requests and responses every 1/3 of a second, and we measure the delay seen by the client in a topology where the first pass has a lowest latency, but is completely lossy after 2 seconds. And we see how much time it takes for each protocol to switch from the first pass to the second one. So about multipass TCP, at the beginning it used the lowest latency path, which is expected. Then we have the underverb, so the network that becomes completely lossy. And then you have up to 700 milliseconds to react before using the other pass. Why? So let's take the example of the client and the server. So the first time you have the network which is lossy, you send the packet over the fastest path. Of course, because it is lossy, the packet will be lost. And then, after some time, there will be RTO, and you will say, okay, maybe it's better to retransmit the packet also on the other path. And the other path works, so that's nice. And the packet is received on the server. And then the server has to reply, to send the response, which will be sent on the blue path, because it has the lowest latency. And it discovered that, oh, it's lossy. That's bad. And so it has to wait also an RTO before sending back the response on the right path. And then the client can see the response final. So that's about multipass TCP. With multipass QUIC, actually, we can achieve much better results. We can divide the delay by a factor of 2 or 3. So how it is possible? We have still the case where the client will first send the packet on the fastest path, and because QUIC is nice but not magic, the packet will be lost, of course. And then it has to wait on RTO to retransmit the packet on the right path. But QUIC allows flexible frame definitions. And you can define easily a new frame saying, oh, okay, but the first pass actually is lossy. Don't use it, no. And this information will reach the server saying, oh, okay, first pass is lossy. Let's directly use the second one. And you save an RTO at the server side. So this is an example of how the flexibility of QUIC can provide better results in some use cases. So quick discussion about how multipass can be adapted in the IETF QUIC. So the issue with GQuic today is that the pass ID is in clear text, and so the pass ID is easy to correlate. So it's easy to correlate for a given pass, for a given connection, all the paths that belongs to the connection. So this is bad. Yeah, and then IETF QUIC changed a lot, especially in the Y format since about 2 years. And now we don't have only one connection ID to describe a connection. We have two: source and the destination connection ID. And the core ID apply multipass in the IETF QUIC to use different connection IDs as implicit identifiers for different paths. So how can this work? So first you have a negotiation about the multipass usage via transport parameters during the initial packets. And then you can exchange connection IDs via the new connection ID frame. And you say, oh, this connection ID, I want to associate it to a given path ID, which remains internal. And each host advertises the connection ID the other one can use to reach him. And then, once this exchange is done, the client can use the connection ID provided by the server to reach him on both paths, and similarly, the reply is the same. It's the same in the reverse order. So about the high-level architecture of multipass IETF QUIC, it will just actually include source and destination connection IDs for each path. But the global architecture of multipass does not change. Actually, yeah, we have a few change in the frames where we had a variant with the path ID, which remains internal, and we have, of course, the frames which is related to multipass, address, remove address, and so on. Okay, so these now are a few ideas of what can be done with multipass in general with QUIC. The first one is, yeah, of course, scheduling. So in multipass TCP, we had a lot of work with scheduling, especially to say, okay, on which path I will send the next packet. Now we don't only have one data stream, we have multiple data streams. And for instance, there were a work at EPIC this year that was doing some scheduling to take into account the dependency graph of HTTP in the scheduling to have faster page loads on average. So this is an example of applying some scheduling algorithm to fit with the HTTP cage. Of course, we can apply different scheduling algorithms for other use cases than HTTP. We have the congestion control scheme also, because as I said, we have to use a couple congestion control to remain fair, but we want to remain efficient. And what we observe is that if we have two independent TCP flows that experience a loss, each of them will decrease their congestion control, but on the average, the total, you will lose 1 megabit maybe on the average of both flows. While if you took both the data streams inside a single QUIC connection, today you will hinder twice the same congestion control, the same congestion window, and so in the end you will achieve a lower bandwidth with the same losses, because the congestion window will decrease twice much. Also, there were some tries in QUIC to emulate multiple connection inside a QUIC connection equals roughly 2 TCP connections, but there were some work showing that actually this is completely unfair with TCP. So is it possible to first solve this issue with single pass, and second, to extend it to multiple pass with coupled congestion control? A third one is about on-the-over situation. So how does multipass QUIC works well with real mobility in wireless environments? So especially when you want to prefer the Wi-Fi over the cellular, especially the smartphone case. For this, we are currently running an application which is called Multipass Tester to perform some experiments with mobility. So we force a user to move from a Wi-Fi access point until it loses its connectivity, and to see how well it switches toward the LTE without the application experience too much troubles. And I think the last one. So far, we consider that paths were symmetric. Like in TCP, when you create a path, it is bidirectional. What is about we are using networks that can only flow in one direction? For instance, we can only flow this packet from the satellite, from the server to the client, and then the client use another path, but never replies. Can never send any packet on that path. How to make such use case possible? Of course, yeah, there are a lot of other possible opportunity challenge that might be related to their talk. So if you have your own, feel free to share. And I think that's all for me. So if you have questions, feel free.
So you showed some results for bandwidth aggregation and for handover. You explained nicely why handover works better for QUIC than for TCP. But for the aggregation, why is it that the gains are so much higher if you use multiple QUIC than for TCP use case? Could you maybe elaborate on this?
Okay, so actually, we believe this is related to how we start using the path. in QUIC, in the initial version of QUIC, you can directly use pass. So you just start sending a pass with a pass ID, a new pass ID, and your pass is created. I believe with IETF QUIC it won't work anyway. But you can use directly both paths. While in multipass TCP, you have the handshake of each pass. And this takes time. For the initial pass is SYN, SYNAC, ACK. For additional pass is SYN, SYNAC, ACK, ACK. So it takes at least 2 RTT to start new pass. And if you start, if you use pass not at the same time, the congestion control, the congestion windows will first fill the first pass, and then the second pass is available, I fill the whole second pass, and you have a much more bursty behavior with multipass TCP than in multipass QUIC, and this provoke head-of-line blocking. While in multipass QUIC, we see this issue much less. Yeah.
Have you also done performance tests for IETF QUIC? Do you have an implementation?
Yeah, we have a prototype of IETF QUIC, which works well.
Because there's a lot of talk, and we're testing that out as well, like the optimization of the QUIC stacks is much less than that of the TCP stacks.
Mm-hmm.
So isn't QUIC always going to be slower at this point because the implementations aren't optimized enough yet? Have you noticed anything like that?
Currently, I think with quite slow networks, QUIC could be better, especially when we have losses. When we have a lot of high-speed networks, it will depend. It will need to be adapted, like the context switches you have with the kernel, with the TCP stack, which is much more optimized in the Linux kernel than the UDP one. I know that there are works to optimize the UDP stack, the kernel with UDP cons. Maybe one day we can reach something which is close. Yeah.
Yeah, exactly. But have you noticed a substantial slowdown?
I think there are some work with.
I mean, in a multipass.
No, not in a multipass environment, but in a single pass environment, yeah.
I mean, in the mobile use case, we would. Because it's not. Yeah, it's quite slow.
Yeah, sure.
It's 10 max.
So, somewhat a related question. In your graph, you showed that for some cases, the multi-path was slower than the single path. Do you have an idea of what kind of case that is? Or?
It's always nice to have backup slides. Yeah, actually, so we're looking at, so these are not the same graph exactly. It's a comparison between multipass QUIC and multipass TCP. But actually, we found cases where multipass QUIC will perform much better than multipass TCP, and cases where multipass QUIC perform much lower. And these are quite extreme cases where, for instance, here one pass has a very low bandwidth, while the other one has a very high. And the implementation of multipass QUIC, multipass QUIC is not in Go is not does not behave well actually with such low bandwidth. Don't know why, but
More like really edge cases.
Yeah, those are actually edge cases. But the case that with 77% of the networks, most common networks will fit in the 77% of the case. But yeah, there are 23% which are quite edgy case where, but probably if we tune better the implementation, we can solve this.
Thank you.
Okay, hello everyone. Welcome to my talk about measuring the performance of QUIC. This talk is part of my master thesis where I conduct a user study to find out whether users benefit from QUIC and can perceive a difference between QUIC and TCP. But in this talk, as I said, it's more about measuring the performance. Okay, and I start with the topic with the question, why do we yet need another QUIC measurement, even though there have already been plenty of them published? First of all, current measurements showed usually that the QUIC protocol is superior to TCP, but we argue that often apples and oranges compared together, because TCP is optimized for stability and QUIC is optimized for web performance. For example, QUIC has an initial window of 32 as default and TCP's is 10. And the goal is now for this talk to tune TCP similar to QUIC so that both protocols can be compared. Secondly, there's a difference between the connection establishment regarding TCP and QUIC. QUIC usually does the connection establishment in one round trip time less, and this difference is not really dealt with in current research. And finally, since my talk is going to a user study, I evaluate visual metrics more than page load time, because page load time does not render the user perception closely. Okay. As a foundation for my measurement, I need a collection of websites that is quite small but diverge regarding the content and also the size of the websites. And here I use the collection from the folks of Belgium, from Winchans et al. This collection has 40 domains, and I had to exclude 2 of them because one is their private project page and the other one I had problems with downloading and replay. Okay, for those of you who are inquisitive, this is the complete list. And these are very distinct, ranging from newspapers to articles and very different websites. Okay, since I want to tune the TCP configurations, I have to replay these websites locally in my laptop or somewhere else, and thus I need to download these websites previously. I do so by intercepting a Chrome browser with man in the middle proxy and download the websites. Basically, man in the middle proxy stores all HTTP responses to disk that it encounters and also saves the IP addresses where the responses come from, together with the URL that was used by the browser to request these resources. Okay, here is a quick plot about how the distribution of the websites looks like. We have websites with very small size and also many true ones that are quite large. And also what is interesting today is the distribution of the IP addresses that need to be contacted for one single website, because websites comprise a lot of elements today, and thus a lot of servers need to be contacted. Okay, now towards replaying these websites locally. There is luckily a framework, MyNI, that does a lot of the work already by spawning one server for each IP address encountered, but indeed MyNI does not support QUIC. Also, we want to support latest TLS 1.3, and thus I exchanged the servers, Apache server with an Nginx server and a Google QUIC server inside the MyNI framework. Luckily, also my comes already with an interface for changing the network towards the application, and I use this network stack here to emulate different network conditions for the measurements. Down below, there is a Chrome browser that accesses the website through my and I use this browser time to record videos of the loading process of each website to later on evaluate for the visual metrics. Okay, before I start the measurements, I conducted a very short benchmark to test whether the two implementations are actually perform about the same. So the TCP configuration and the Nginx Google QUIC configuration. And therefore, I downloaded a single file of varying size 31 times. And as you can see, only for large files above 10 megabytes, there is a noticeable gap between Nginx and QUIC. But my resources for the websites are usually much smaller, and the largest one is about 4 megabytes, so this should not impact our measurements here. Okay, regarding my network configurations, for this talk, I concentrate on these 4 settings. I have a speedy DSL broadband connection, like you would expect from your home, a slower LTE connection, and the last 2 are something special. These are measured from in-flight internet service. So if you are lucky on the plane and you have internet, these could be the values that you get there. And the DH2DC network is direct air-to-ground communication, and it bases on your mobile internet, but with antennas pointing towards the sky. And the second one is MSS, mobile satellite service, with, as the name suggests, the satellites to provide internet to the plane. Okay, as I said in the introduction, it is not that easy to compare QUIC and TCP right out of the box, because QUIC is a little bit different configured. These are some stats usual TCP, TLS, and HTTP configuration would have right out of the box. Initial window 10, we have handshakes for TCP and TLS encryption. Depending on the server, you have HTTP 1 or 2, and of course, we have head-to-line blocking. QUIC, on the other hand, is positioned much better. And the goal is now to close this gap as tightly as possible to make the measurements fair. At first, setting the initial window to 32 as well is quite easy. And we can also use TCP fast open and TLS 1.3 with 0 RTT. But a little downside here, I won't do so in this talk because of the following reasons. At first, TCP fast open is very used in practice today because of middle boxes hindering the deployment. And sadly, for TLS 1.3 with 0 RTT, this was not implemented in the Chrome browser at the time of measurements. But also in my setup, QUIC is not 0 RTT capable because I always use a fresh browser profile. Still, there is a gap of 1 round trip time, but I will deal with that later on in my talk during the evaluation. Okay, finally, in my testbed, I fixed to use only HTTP2, and head-of-line blocking, we cannot do anything about it. So this leads me then to these following 5 protocol scenarios I will deal with in the talk. For comparison's reasons, I have a untuned stock TCP configuration, like you would have right out of the box. And then there's the tuned one with the enhancements from above, and also using pacing and some kernel treatments to buffers. And since we expect the congestion control to have a huge impact on network performance, I implemented also for both TCP and QUIC a case where BVR is used instead of QUIC. Okay, since I don't know how familiar you are with visual metrics, I have a short recap on them. This is the loading process of a website, and you can see the visual completeness over the complete time. And visual completeness is roughly how many pixels correspond to that frame to the final picture when the website has finished. And from this one, I derive 5 metrics. First visual change, last visual change, and page load time. That should be quite intuitive to understand. Note that sometimes, or like in this example, page load time can also occur in front of last visual change because of JavaScript popping up some elements or whatever. Then I have the visual completeness 85% mark, where is the point in time where the website looks quite finished. And as a evolved matrix, the speed index, which should render user perception quite good. And this one is calculated by taking the integral over the area above this visual completeness line. So it favors websites that already look finished quite early. Okay, last thing before I come to my measurements, I have a short teaser for a video for you where you see one website and all the 5 protocols side by side. As you can see, QUIC is indeed fast here, but especially there's also a noticeable gap between untuned TCP and the tuned TCP+. So I think TCP+ should now be ready, where the untuned is still loading, showing that TCP tuning can also directly lead to performance increasements. Okay, a short recap. I evaluate 38 websites under 4 network conditions that get replayed in my framework, and I do so for 5 protocol scenarios. Each measurement gets repeated 31 times for statistical significance, and I evaluate the 5 metrics. As a metric, I use performance gain, where I compare one protocol, a reference protocol, regarding a different protocol. And here I consider means of some metrics, and this is basically the normalized difference between 2 protocols. Okay, now towards the results. This is the plot for the network of DSL, and here you can see the baseline is set for the untuned TCP protocol at 0, and all the other lines then are calculated performance gain regarding the TCP reference line. And each line is a CDF representing all 38 websites. So if the plot is to the TCP plus and TCP plus BBR lines are towards the left of our reference line, then the tuned and TCP BBR is faster here. So what you can see here directly is that tuning improves the performance of TCP already. Nevertheless, the congestion control does not seem to have a huge impact here because both lines are very similar. And now regarding QUIC, this is a little bit different. Here you can see directly QUIC is still better than even our tuned TCP, but the gap closens. Also here, the congestion control is not that relevant, but you can see that the curves are quite steep in this graph. So we think that this indicates that the website structure seems to have little impact on the achievable performance gain. Okay, since performance gain here in this plot evaluates only on the means of these 31 ones, we wanted to know whether there is also a significant difference between 2 complete distributions of these 31 ones. And therefore, we choose to evaluate an ANOVA test, which can tell for 2 sets of measurements whether they originate from the same distribution or not. And when we do so, here's an example. For the first rule change, we classify which protocol was significantly faster. So here for TCP, the tuned variants, 28 websites were significantly faster. And for 10, we cannot classify because the test doesn't tell us. So. And in this table, the cells are marked green if the majority of the websites is faster for the protocol that we think should be faster. So QUIC should be faster than TCP, and also TCP plus should be faster than TCP. And red, we mark the cells red otherwise. And yellow if we cannot tell because the test doesn't tell us. Okay, and these are the complete results. As you can see, throughout all metrics, the results are the same. Basically, the protocols are faster if we think they should be faster, and also the congestion control does not have a significant impact here. Now, regarding, what I forgot is that the LTE network here yields exactly the same results with some different numbers, but the message is still the same, so I will leave out LTE here. Okay, regarding the slower in-flight networks, and this is where things get a little bit more interesting. Here you can see again, QUIC is faster than TCP somewhat, but the congestion control here has a much higher impact. When you follow, for example, the green line for TCP with BBR from the left to the later matrix to the right, you can see that TCP with BBR gets even better during the loading process, whereas TCP with QUIC stays about the same. And for the page load time, you can see that both BBR variants are quite same, whereas the QUIC variant with QUIC and TCP with QUIC are indeed slower. So this shows that the congestion control here is much more important than the protocol choice. Also, yes, that is. Okay, finally to the last network, which is the direct air-to-ground communication. Here we can, for the first time, see that there's not a huge difference for the TCP configurations, and tuning did not have a huge impact here. And we think that this is the case because the bandwidth available in this network is quite low. Nevertheless, TCP is still outperformed by QUIC again. And for the first time, we can see here in the page load time that QUIC with QUIC indeed could also be a little bit faster than QUIC with BBR. One interesting thing you can see here is that we have hard outliers for speed index and visual completeness, 85% towards the left, and also above towards the right that already get cropped in these images. And this is because some websites load very distinct regarding both protocols, and thus speed index and visual completeness fail to render these measurements. Here is a little bit closer look up into this. This is the New York Times website, and as you can see here, quite obviously QUIC is indeed faster than TCP regarding page load time. But for the visual matrix, visual completeness, 85%, there is still a large gap in between. So TCP is there faster. And let's have a look why this is the case. And I'll show you now two screenshots from the time in between of these both visual completeness events. As you can see here, there is a banner on top of both websites, and this banner changes their height during the loading process. TCP manages to load the banner early instead of QUIC, and QUIC loads the lower elements first. So in TCP, all elements are already placed at the final position during loading process, but QUIC, this is not the case. And due to this misconception of the visual matrix, this is a motivation for my user study that I also conduct currently. And I will go briefly through the design of this study. We have two surveys. The first one, we ask users to watch the videos like you saw. And here you have two protocols side by side, and you should decide which one you favor. But since this one doesn't tell us anything how large the gap between the perceived difference is, there's also the second study. Here you can see only a single video, and should rate on a linear scale how much you like this video. And with this study, we can measure how big the gap is for users, or if there is a noticeable difference at all. Okay, what is still left from the introduction is the gap between TCP and QUIC regarding the connection establishment. As you can see here, for TCP, we have roughly 2 round-trip times that need to be done before actually the HTTP request can be sent out. Whereas for QUIC, in my setup, I need only 1 round-trip time. And the idea is now to subtract 1 round-trip time from the measurements for TCP, and then compare the results again. Luckily, in my testbed, there are 2 websites that rely for the resources on a single server only. So here for these 2 websites, only a single connection is established, and thus the difference can only be 1 round-trip time between the 2 protocols. So these are the results when subtracting out this 1 round-trip time difference, above for TCP tuned versus QUIC, and below, since the congestion control has a huge impact for the NSS network, I concentrated on the PBR cases here. And you can see the difference in milliseconds as well as the difference in round-trip times measured for the metrics page load time. And as you can see here, the difference gets very close and far beyond below 1 round-trip time, so that there isn't a huge difference between TCP tuned and QUIC anymore, when also taking the round-trip time and connection establishment into account. Still, TCP fast open and TLS 1.3 would close this gap, but remain challenging to deploy. And the remaining gap, for example, for these lossy networks, also we think that this could be due to circumventing head-of-line blocking in QUIC. Okay.
So which number is negative?
Negative is better for QUIC. So this minus 400 milliseconds QUIC was that amount faster. Okay. I started my talk by motivating why we yet need another QUIC measurement, because current measurements have not taken the TCP configurations into account. And I realized this by downloading websites replaying them in the modified MyMy framework and tuned TCP parameters. The results are that tuning TCP is not negligible, and still QUIC outperforms even our tuned TCP, but the gap gets narrow, especially when considering the connection establishment. And also in some networks, congestion control seems to matter more than the protocol choice. And thus I end my talk by once again promoting my user study. Please participate and feel free to distribute the link towards your friends or colleagues. Thanks. Are there questions?
The study is also coupled to the free lunch, but
Okay. Yes.
I was wondering if you have some initial results from this user study.
We are currently
indication that people think it's faster.
We are currently evaluating this, but the results is roughly that when you see TCP and QUIC side by side, you can perceive a difference. And even though these are sometimes some 100 milliseconds that the difference is, but when you see only a single website, we currently cannot really see that users prefer QUIC or even see a difference at all. Even, at least for websites that have in the slow networks seconds, where the difference is seconds, then maybe, but not really when you encounter a random website and have to wait for performance. Yes.
I'm actually interested in this congestion control part. So did you even see congestion? Did you even see any losses when downloading a webpage?
We don't have any concurrent flows here in, so there's only the congestion due to buffers filling up, and also the loss that is in these networks, the slower networks, is quite high. So I think that is more to BBR, which can oversee random loss in these networks compared to QUIC, compared to QUIC, because QUIC interprets random loss as congestion, and BBR can fill the pipe nevertheless.
Did you collect any loss statistics?
I have, but I haven't evaluated, so I would have PCAPs to look inside. But yes.
Have you considered, in one of the screenshots you showed the ad difference because of the ad loading? Now have you considered doing the same test, really blocking all the ad scripts, because the ads typically don't, are maybe not even on QUIC because they're from another domain?
Finally, there is one part that I left out here. Replaying the advertisement is not possible because usually the advertisement is requested with a random string in your URL, some timestamp or something like that. But doing recording, I only record one snapshot. And then JavaScript for the advertisement generates a new random string, and this one cannot be found in my collection. So basically, I don't have ads in my websites doing replaying, but some stuff like this can also occur. Thank you. Yes?
For a user study, are you doing like live page loads, or are you record videos of page loads?
these are exactly the videos you saw in the demonstration. So we show fixed videos of certain scenarios in these network conditions and no live logging.
Thank you.
Okay. Wait. Okay. So first, a disclaimer. If you read real-time media, you might think of video conferencing. I have to disappoint you. My talk will not be about video conferencing, but mostly video on demand. But what I say in this talk is almost always also applicable to live video streams. But yeah, not video conferencing. So first of all, I think we can agree that video streaming over a reliable protocol like TCP is a bad idea. And I want to claim that streaming video over QUIC, which is also a reliable transport protocol, is also a bad idea. First, why do we even care about streaming? Well, streaming is everywhere. It dominates the traffic of the internet. And according to Cisco, it will only increase in the next years. However, due to CDNs, video is currently still transferred via HTTP, so over TCP, again, reliable protocol. And one requirement for CDNs is that all the intelligence has to be on the client side, because CDNs deploy web servers and they do not really like if you need some extra intelligence that would need changes to the web servers. So why don't we just try to improve TCP? First of all, yeah, TCP is in kernel space. Many people do not really like to hack in kernel space. And on the other hand, QUIC is starting to get deployed. And even Google is delivering more than 40% of its content via QUIC. And this includes the YouTube traffic. So QUIC is getting important. And also CDNs already start to support QUIC. Now, we all don't like this one, yet if we transfer video via QUIC, we will still see this one. So why is this the case? Again, QUIC is a reliable transport protocol, so QUIC inherits all the issues that TCP already had for streaming video. To show that this is really a problem, we conducted a simple experiment. We have a server, a simple HTTP server. We have a shaper in between with which we can control the link conditions, so bandwidth, loss, and so on, also the buffers. And the client is requesting the video. In our case, we transferred a typical 1080p video, and the bandwidth that is shaped is large enough to accommodate the stream and even having headroom for potential cross traffic. However, when we ran the experiment for varying loss rates, we see this. On the x-axis, you can see varying loss rates, and on the y-axis, we have a metric called rate buff, which indicates the number of stalling events compared to the number of video frames in the video. That means, for example, if we look at 0.16% loss, we see that QUIC has almost no stalling events. So stalling events are events when the video stops playing, you see the rotating spinner and you cannot continue watching. If we increase the loss rate to 0.64%, we can see TCP spends almost half the time the video, half the amount of video frames we spend stalling. So pretty much every second frame we would see the spinning wheel and then the video would continue. We see again the spinning wheel.
Can I ask you a question? Which version of QUIC did you use?
In this case, we used the quite old-ish version of Google QUIC, implemented in QUIC Go. I will cover that later. We now switch to a more modern version, the latest one in Chromium we have now. But those experiments were still the old one.
And are they both using QUIC?
Oh, this one is using the QUIC variant, so no BBR here. Okay, yeah. As we heard in the talk before, QUIC is supposed to have no head of line blocking, and it should solve the stalling issue, but it doesn't. And we also heard in the talk before that, for example, in-flight Wi-Fi has loss rates of more than 3%, and we can see, yeah, even at loss rates below 1%, the performance is bad. We conducted a different experiment. Now we consider the durations of the stallings compared to the pure number of the stalling events. In this plot, you can see how long it took to transfer each video frame. So the green shaded area are frames that were transferred fast enough for fluent video playback. Precisely, they were transferred faster than the frame rate of the video. And you can see even with, again, the 0.16% loss, which is very low, that TCP is not able to transfer all frames in time. However, in this case, QUIC, the Google QUIC, is performing quite nicely. If we increase the loss, then also the performance of QUIC degrades, and TCP is pretty much struggling very hard. And lastly, for loss rates beyond 2%, both graphs pretty much fall flat on their face, and yeah, the amount of stalling is so high that fluent video playback is pretty much impossible. Okay, why is this? First of all, TCP. We heard this before, TCP encounters head of line blocking. So pretty much if we have a loss, we have to wait for the retransmit, and every further data is not yet useful for us because we have to wait. And again, TCP is a reliable transport protocol. So even if we manage to finally retransmit the data, it might be way too late because the player has already moved on beyond those frames that are retransmitted way too late. Now, if we replace TCP with QUIC, we do not have head of line blocking in general. However, we have to transfer the video chunks themselves. So those transfers still encounter head of line blocking. Again, reliable protocol, we have to wait for every single byte in the transfer before we can move on to the next frame or next chunk in the video. So again, pretty much QUIC inherits all the problems that TCP already had. What we now propose are unreliable streams. That means we do not want to retransmit data, but we want new data. So we want to allow losses in the video frames, because we think that if we transfer new fresh frame data, it's better than having stale old frames that might not even be played, because the time has already passed beyond this point of the reception of old frames. However, we do not want to touch QUIC's ACT mechanism, because we still want to have the possibility for the server to know when packets arrive and when not. So we do not want to have a UDP implementation on top of QUIC. As well as we don't want to mess with the flow and congestion control, because congestion control is hard, and if we remove congestion control and move back to some sort of UDP-like stream, we would overwhelm networks. We don't want this. We want fairness between TCP flows and QUIC flows. So we need those unreliable streams still to be congestion controlled. We also want to have those unreliable streams to be negotiable during the handshake. So if, for example, a server or client is not capable of using unreliable streams, it should seamlessly work like before. And that's why our proposed unreliable streams should be an extension to QUIC, not a modification. So we want to keep as many features of QUIC intact and only change what we really need to implement unreliable streams. Especially right now, as QUIC is changing so much, it's a good idea to have it as independent as possible, so we can still work on different versions of QUIC, like our switch from the old Google QUIC to a now newer version. We are not the first ones to try to implement some sort of partial reliability. For example, the folks at Akamai, they proposed a partial reliable message streams for QUIC. And they proposed that servers can indicate stream offsets that are meant to be expired, meaning data that is older than this stream offset will not be retransmitted. Yes. The point for us is here that this offset is given by the server, if I'm not mistaken, and it would be, in the case of video streaming, quite challenging for the client to determine which point should we set to be expired. And yeah, sorry. Okay, a different approach are the unreliable datagram extension to QUIC. This is as well the IETF draft from Google and Apple folks. They try to implement UDP-like streams on top of QUIC. The idea is similar to ours, meaning you have no retransmissions, but they propose to have really UDP-like streams, so no flow control and no congestion control. Besides, the whole connection is still congestion controlled, but you can fill up the queues as fast as you want, so there's no preventing a simple client from overwhelming a network again. And there's as well no indication for a stream end. So why this is important, I will tell you in a minute. A third approach is the real-time audio-visual media transport over QUIC. This is work from Colin Perkins and Jörg Ott. And they want to map RTP functionality to the QUIC world. They introduce a new frame type, RT streams. It's a different approach because they focus more on the video conferencing side, where you have video frames small enough to fit into one packet, which is not the case for our use case, which is large videos that span over multiple QUIC packets. Okay, so again, what do we do differently? As I said, we try to modify QUIC as little as possible to be able to easily switch implementations and cope with changing of the QUIC protocol. When we first implemented this, the Google QUIC version we used, the wire specification had no space left to add new frame types, so we had to reuse the stream IDs to indicate if we have a reliable or unreliable stream. Now there is more space, so it might be a good idea to simply use a different frame type as well. However, there are also the unidirectional streams, which also use the stream ID space for indicating a bidirectional or unidirectional stream. So using the stream ID for indicating an unreliable stream might not be the worst idea. And as I said, we do want to explicitly indicate when the stream ends. Why do we need this? If we transfer video frames or video chunks, the client needs to know when did the server transfer, or at least attempt to transfer the video frame or video chunk in full. Otherwise, we have to wait for a timeout, and that means wasting time. If we explicitly notify the client, okay, I at least tried once to transfer the video chunk, pass it to the application, and the application will do whatever it wants. That's better than wasting time in timeouts. Okay, now if we implement all of this, we have unreliable streams and everything's fine. No. The problem is if we just transfer the video completely unreliable, meaning our approach that still is congestion controlled, we would still result in this. Because if the full video is transferred unreliable, we would encounter a lot of degradation in the video quality, which is undesirable. So one challenge is to multiplex the video, meaning, yeah, which part do we transfer reliable? Because QUIC allows us to have more than one stream, so we can say, okay, this part of the video I want to transfer reliable because I think those frames are important. This part of the video might not be that important, just try your best and transfer it unreliable, and we will receive whatever we will receive. In our case, we tried one solution that is pretty simple. We transfer the keyframes, so the full picture is reliable, and the rest of the video we transfer with best effort, and it will receive what it receives. In the case of HTTP streaming, HTTP video streaming, we are forced to have keyframes in regular intervals. So even if we lose this nice stunt of the bicycle driver, we would still have the next keyframe, and all errors in between would just be covered up. Yeah. Okay, a different problem is now that we allow unreliable transfers of frames, we have holes, meaning that we transfer frames only partially. And how do we fix this? Because if we transfer half video frame, what will the application do with this? One approach is to simply tell the application, okay, this frame is only partially received. Another approach is to just pad the missing data with zeros, because in QUIC, each QUIC frame has an indicator of the absolute position it would have been received, meaning we know exactly how large the hole is, and we can either tell the application, okay, there was a hole this big, or we can pad the hole with exactly the right amount of random data, zeros, or ideally blank video frames. Yes. Now that we have several QUIC streams to transfer the video, we have to reassemble the video. In this case, we would have one QUIC stream transferring frame 1 and 5, and the other QUIC stream transferring the rest of the video. So how do we reassemble the video? Another challenge is we not only have to know how to reassemble the video, but QUIC streams are not related to each other. So we cannot guarantee that frame 1 is received before frame 2. So we have to know the order of the frames as well. Again, the challenge of indicating when a stream is done, meaning when a full chunk of video is transferred, which translates to the question of when can we close the stream, when can we transfer the video data up to the application? Yeah, the reception of the fin bit. But what if the fin bit gets lost? Then again, the video player has to wait for either a timeout or some other heuristic to know, okay, the server tried to transfer the video chunk in full, and I can start to decode it. Again, we try to modify QUIC as little as possible. So we just said, okay, simply transfer the last QUIC frame reliable again. So we know exactly, okay, server tried to transfer this video chunk. Once it is done, we can pass it on to the application. Okay, in summary, we want to state that streaming video over vanilla QUIC is not the best solution. Introducing partial reliable transfers is not trivial. There are several challenges on both the transport layer and the application layer. Our solution for this is to have a most simple extension to QUIC in order to have unreliable streams, so we can transfer our videos with partial reliability and only transfer, again, important parts reliable and the rest in the best effort manner. And we now switch to the Chromium implementation and have a full end-to-end setup, including adaptive bitrate schemes and all the bells and whistles. And yeah, we right now start to conduct experiments on evaluating the performance of this implementation. Because we had quite a few issues with the old Google implementation in QUIC Go. So now we are at least at a point where we have a reliable QUIC implementation and can start performance evaluations. That's it.
So typically you do buffer a bit at the time, right?
Yep.
So what would you do if you transmit frames unreliably and you have a loss, but you will have time to actually retransmit it? So, I mean, in the end, if you retransmit it, there's no gap in the helium, right? So how would you decide, or when would you decide to retransmit that frame, or how would you actually do that?
For this, we want to use the adaptive bitrate algorithms because they take care of filling the buffer. And if we, for reasons of loss, congestion, or whatever, are not able to fill the buffer, then the ABR would know, and then we can switch and see, okay, lower quality. If we have little enough loss, we can just deal with this, or we can start to use forward error correction to cope with the loss, to keep the buffer amount high. So yes, you would not see immediately an interruption, but your buffer would be drained if you cannot keep up with filling the buffer.
But that's because your AVR algorithm applies only to future packets, not the ones that got lost, that cause your packet to get ready. So can you be smarter and like reduce the rate of packets that were lost that are causing a buffer to get to deplete?
But how would you? So do you mean that the only possibility would then to lower the quality to?
Yeah.
But this is undesirable. So a lot of studies showed that people prefer the higher resolution video to the lower resolution one. So compared to having artifacts, so errors in the video. So it's still more desirable to have losses and the higher quality video than switching down to lower quality and then avoiding errors.
Yes, that's debatable, I would say. There's a difference between quality switches and having stalls. I think stalls are
the most severe. Yes.
Thing, I guess, you can have.
Yeah.
But of course, quality variations are also not preferable, I agree. But if a quality variation could help you prevent having a stall,
but
I think there's still a...
This is true, but our approach also avoids the stalling because we trade off stalling with errors in the video because we do not wait for retransmissions, we just go on. So we have byte errors and we trade this for not having stalls. Mm-hmm. And we claim that this is still the better QE than switching down to a lower quality level.
That would be my follow-up. Did you test this already? Do you know this? Because it could be the case, but...
So far, everything indicates yes, but we are just starting to conduct the experiment, and ideally we want to conduct user studies, but let's see. So we hope to confirm our initial intuition.
Small question from a guy who is not really into video streams. So do your use case target application like YouTube or Netflix?
Yep.
Okay, in the beginning, you showed different graphs with different losses and very high rebuffering percentage all the time. But so far, from what I know, at least, like YouTube and Netflix are popular services that are using TCP or QUIC. So, is there a difference between your experiment and what they are using?
Yes and no. So the experiment that I showed is really the most basic one, no quality switching, just one transfer. So Netflix and YouTube are doing quality switches and so on, but we wanted to show if you have enough bandwidth to stream a 1080p video, you're not able to if you encounter losses. So yes, YouTube has more sophisticated algorithms, but this is what I mean with the ongoing work. We try to replicate all the algorithms that Netflix and YouTube are using, and so far we can still show that vanilla TCP, vanilla QUIC, and the switching algorithms are not enough to transfer video without stalls, even if you have sufficient bandwidth, due to the losses.
Did you? So I don't know for Netflix, but last time I looked by accident almost at a YouTube matrix. I think they're using 2 minutes buffer size, something like this. So is this the reason why we don't see losses?
Yeah, sometimes, yes. If you have large buffers, then you can deal with more varying network conditions, because you have enough time to rebuffer the stuff. But as I said, we also want to target live video streams, and there you cannot have 2 minutes of buffer.
Yeah, sure, but the intro was a bit confusing because it was counterintuitive to show that TCP and QUIC are not able to stream video, meaning for YouTube or Netflix, while those services are very popular and making so.
Yeah, but they only work nicely if you are sitting at home and have a stable connection. If you're on the go or in an airplane, you can forget streaming video.
Yeah, then maybe those are practical settings you should investigate and maybe compare with. I don't think the solution, your solution and their solution, if you could put a separation between the two, meaning one are using buffers, you are using unreliable streams. I don't think those are, they cannot be combined. I don't think let me state it clearly. I don't think we should choose one or the other.
Yeah.
We can combine them.
Yes,
And
this is our goal.
that's the way forward, because streaming videos from Netflix without using buffers or very small buffers is not realistic. That's what they do.
Right. So we want to combine both. The point is that we claim that we can deal with even lower buffers. So we want buffers, but we can make them as low as possible to be able to have live streams and to reduce the initial startup time.
Yeah, then maybe it's an evolution of the cost of the buffer. If you are doing live video conferencing, the buffer is costing a lot in terms of user experience. If you are streaming a film from Netflix,
but still, for the YouTube case, people don't want to wait to the video to start. So if we can increase this metric, a lot of people would be happy.
Okay. Thank you.
Okay.
Question: is this part of is it part of the browser, or was it accessible from the client go to the JavaScript? For example, in YouTube, that the streaming it happens in the JavaScript code and not in the browser code. But I guess this would be something that's in the browser, or
so our unreliable streams and the dealing with multiplexing and demultiplexing is more or less a shim layer above the transport and in the transport, and we wrote it in a way that it's possible to use the browser and JavaScript to request unreliable streams and have a normal HTML5 video player and make it capable of using unreliable streams. In our testing, we separated all of that and just use Chromium as a server and a headless Chromium client, and that one is just utilizing adaptive bitrate algorithm that we got provided. And there's no rendering, no JavaScript, but the idea is the same, and you in the end could deploy all of that in the full browser using JavaScript.
I was also asking, maybe user wants to have more buffer instead of.
We could expose those knobs, yeah. But ideally, it should be automatic because most users don't really know what they're doing.
Given an explanation, why didn't you choose for IETF QUIC?
Because after the QUIC Go implementation, we wanted to have a full browser to be able to, in the end, have a full end-to-end setup, including a JavaScript player. So we chose Chromium because it's a very large and popular browser that has a seeming stable implementation.
You're not using it right now, and by the time you will be using it, maybe Chromium will have the IETF QUIC.
Yes, that's why I stated a lot of times that we try to have this as an extension to be able to quickly switch implementations. And yes, right now I saw that the Chromium people are switching the QUIC implementation to an IETF one. So we have to deal with this again. But I hope that we have separated our modifications enough.
Maybe one final question. You showed multiple streams for the same video segment with different picture frames for different streams. I just want to add, I used HV2 in the past for video streaming, where we would push one file segment at a time, let's say, with a different stream. What type of encoding did you envision or do you plan to use? Because traditional adaptive streaming, you would have one single segment, send a request, get a segment, then go on to the next. What did you use here, or what do you envision?
We use and envision pretty much this, and that's the whole problem. In HTTP video streaming, we have a chunk as an opaque object, and we request this once. So all the trouble of head of line blocking and so on applies to us. That's why we propose those unreliable streams to more or less separate the chunk again to request parts of it reliable and parts of it unreliable. But we still want to stick with it's a chunk and we request it via HTTP, just not anymore as one HTTP request, but several range requests in between to split them onto several streams.
So there's another approach which was at least mentioned in the idea, because it's not focused on the idea here, which is just sending one frame per stream, because streams are super cheap and you can reset a stream so you don't need it anymore. So it will be transmitted reliably until you say I don't need it anymore. And then you can
This, we thought about this, but then you need some sort of control stream again, because if you split the video into one frame, one QUIC frame, then how do you reassemble them? Because then the order would be lost. So this approach does not need an additional control stream because we request.
So it's just so I guess it's easy from your implementation to expose the stream ID.
True.
Not all implementations do that, but they could.
Okay, if we do this, we could keep the order. Yeah, might be worth investigating. Okay.
All right, fantastic. Thanks everyone for the talks. This is the end of the AM. So we're about 10 minutes late now, which is fantastic. I propose that we just cut lunch short by 10 minutes as well, and we just start again at 1:30. So we have 50 minutes for lunch. I think lunch is served. There were some problems with the coffee. There is some coffee, but maybe not for everyone for 5 cups at this point, but they're making new. So by the end of lunch, there should be plenty of coffee to last you through the afternoon. If there are no more questions, then please. For the people who have filled in the surveys, there is lunch. Thank you.